Hi and welcome back to a new video. And finally also the Ryzen 7000 launch content. We had these CPUs for several weeks. We enjoyed playing with them, enjoyed doing development for new products because AMD finally moved over to an LGA socket, which allows to do a lot of modifications which previously were not possible with the PGA socket. So initially when I just had the CPU the first time, I straight thought of, hey, what's up with direct eye cooling? What's up with delidding? And even though a lot of people thought that with the very special shape of the IHS, delidding will be impossible, I can tell you it's not impossible. We found a way to do it. And in today's video, you will see how we went through the development phase of delidding and also direct eye and what kind of results you can expect. And I can tell you, those results are absolutely insane. We will first look at our Ryzen 9 7900X. It's a 12-core CPU we had for development, and we will inspect first some just stock runs to see what kind of thermals and what kind of clocks we can get out of the box. We are now performing a test run with the 12-core manually overclocked to 5.4 GHz across all of the cores with a core voltage of 1.29 volt. And it's also the required vCore I need for getting this clock stable. Definitely losing a bit of performance due to having CPU-Z and also hardware info open in the back, but we can see the peak temperature was just above 90 degrees Celsius. This is our current test setup for our temperature testing. We're using an ASUS Gene board. It's an engineering sample. You can see there are like no chipset coolers, no VRM coolers, nothing on there. That is what you get when you have like those very early test samples. And we are testing with the Corsair water block and a 360 pretty much custom water cooling combination. And the 5.4 GHz I just showed for the temperature run are also the maximum we can run right now with this configuration or this CPU. You can see if I set it to 5.45 across all of the 12 cores with this voltage and temperature, we are really on the limit. So this pretty much crashes instantly, while I can constantly run the 5.4. So that seems to be the edge for the CPU. Delidding an AMD Ryzen CPU is one thing, but also reliably delidding it without damaging the part, that is a different thing. We made this prototype delidder in CAD, and at least in CAD everything works out fine. We have a CAD file also from the AMD Ryzen CPU from AMD, but strangely the placements of the SMDs are a bit different to what we have here on the actual sample. Yeah, that's why I hope everything will work out, but I guess there's only one way to find out. The delidding process should be the same as pretty much all the other delidders we made so far, just using shear force from the side and metal fatigue. We have our AMD Ryzen CPU, and because of the strangely shaped IHS, we made the slider also a bit different to what we had in the past. We have those 4 notches coming out of the slider. Don't worry, like all of those are prototype parts. The like serial production parts will be a bit different, but this should work just fine for testing if this even works. The plan is that basically the slider fits onto the AMD Ryzen CPU, and then we will use the slider to push the IHS slightly back and forth, like left and right. Because if you just check here, there is a space of about, or like clearance of about 1.8 to maybe 2 millimeters, and that should be sufficient to just move it a little bit to left and right, and after maybe 10, 15, 20 movements, we will find out. The IHS hopefully comes loose without damaging any of the other parts. This means we start with the CPU first. Obviously pay attention to the orientation of the CPU. That will be very important because they are differently shaped. Put in the slider. Now fix the slider with these screws so it cannot like go up to the top. Now we have 2 ball bearings, left and right, because the plan is now that I will tighten this screw. It will pull the slider about 1 millimeter to the left. Then I will remove this one and tighten the screw on the right and then pull it a bit to the right. At least that's the theory. But again, this is a prototype, so the bearings would be different in the final one. After the second pull, we can already see that the IHS moved slightly to the bottom, and there's still enough clearance to these like SMD parts next to it. So that looks already nice. Okay, so if I cannot pull it by hand, then I will definitely know that it's still quite tight. first look, I'm very satisfied. At least from what I can tell right now, like just inspecting all the SMDs and like the edges of the die and everything. No damages. And in the end, that's the only thing that counts. So yeah, I will clean the CPU and then check back. Onward we go with our development of the direct die frame. Prior to this, we received CAD files from AMD, which included both the socket and also the CPU. But we noticed then during our development phase that the CAD files slightly differed from reality, especially talking about the capacitor placements underneath the heat spreader. That's why we decided to use our own 3D scanner and then get a proper scan of the CPU. And you can see this is very accurate. You can even see the residues on the chiplets, which are still residues of the indium solder. And around that you can see those round points, like those were the black points, the residues of the glue that is holding the IHS in place during the soldering process. So it's very accurate. And based on that, again, a few days later, we had the first draft ready of our direct die frame. Then we only had to do the CAM simulation, so that's pretty much writing the program for the CNC mill, and we can continue with production. The CNC mill is now equipped with a 6mm aluminum plate to make the direct die frame, at least the first prototype. If we would do mass production, you would probably switch to a 4mm plate simply because we wouldn't have to thin it out, but yeah, that's just for the first try. At least one side already looks great. So now the only remaining thing we have to do is manufacture the top side, and I mean, just looking at how this is clamped into the vise, not quite happy with it. Would be much easier if we would have any kind of like mounting mechanism where we could mount it over those 4 screws or like 4 holes, but I hope it will just work out. For the final direct die mount, we have to prepare our 7900X. Simply, we have to remove the glue residues and also the indium solder that is still left on the chiplets. We could use some liquid metal to do so. You could use any liquid metal to do this. Just the gallium inside the liquid metal, if there's plenty inside and you have plenty of material, leave it on there for like 5 minutes, should be enough to solve the indium. As alternative, you can always use a sharp object like a razor blade to scratch it off. Making good use of my Delidding 12900K, but before people freak out again, the 12900K is dead anyway, so. And that's the result you should expect with the cleaned dies and also with the removed glue around it. Next up, we will have to remove the AMD SAM. So the thing which originally keeps the CPU inside the socket. Unfortunately, AMD decided to kind of fix the screws inside the SAM, which means that we cannot reuse them for our direct die frame, which is what we typically did with Intel, because they have UNC thread and then you want to just use the same kind of screws to still keep the original backplate. But that's something we cannot do. We will still keep the original backplate, that's all fine, but it means we will have to get our own screws made. So now, CPU into the socket. And now you would place the direct die frame on top. Since this is still a prototype and it's not anodized, it means that I will have to cover the contacts that I have underneath on the board. For the retail unit, like for the retail direct die frame, it will be anodized, which means that it will not be electrically conductive and you should not have to like tape those tiny contacts. I simply put some Kapton tape on top to protect these SMD pads and that should be fine. And now we will put our frame on top. Those are not the screws we will use for the final product because the height of the screw head would be too much. So I had to grind them down a tiny bit. It's important to now check if the cores are actually the highest position. And that's right, because left and right you can see a tiny bit of shadow underneath this metal plate. It is really important to check that on the first attempt, because otherwise, if the cooler sits on the frame and not on the cores, then your CPU can easily die. But going back to my case, the direct die mount. I could not mount the CPU block from Corsair simply because the die is now sitting so much lower than previously with the original IHS. So I couldn't use the original backplate anymore. Decided to make my own one. So that's made out of aluminum anodized, and it's basically following AMD spec, and it's just shorter. So I call it the AM5 short backplate. Very creative, I know. But this should allow compatibility to other coolers, maybe also to the EKL cooler, not quite sure, but also for extreme overclocking if you want to use your liquid nitrogen container. And typically then we use M4 rods, just threaded rods, through these holes right here. Then you can just make use of the short backplate. We're also going to make this available. So hopefully now I have everything prepared and hopefully can finally mount the cooler. So my solution for the moment right now is I'm going to reuse this EK backplate, which I also modified from a different project. Cannot remember why I cut this part right here, but I put some M4 screws. Those should be from a Corsair radiator through them. Well, that should work just fine. And then my plan was to just use this like typical Acetec mounting AM4 whatever plate. And then I noticed this is also colliding with the cap right here, so I will also have to modify that one. So we will simply do a cutout inside our mounting plate. It's also not the best solution because it will definitely lose a bit of like stability, but that's how it goes. Again, a few days later, because I wanted to mount my Corsair water block on the direct die CPU. But that didn't work out, simply because the IHS of AM5 is so high, like so thick, that I couldn't mount this anymore. The stock mounting bracket just wouldn't fit anymore because it cannot compensate the height difference of with IHS versus without IHS. So I had to find a workaround again to make this happen. I think that's also a good point to talk about AM4 and AM5 cooler compatibility, because that's something that certainly needs to be addressed. Just because AMD says that the C height, like the height of your AM5 CPU versus your AM4 CPU is still the same, doesn't mean that all the coolers are automatically compatible, because the mounting mechanism is simply different. For AM4, if you wanted to remove the backplate, you simply had to remove those plastic parts around the socket and then take off the backplate, because some coolers are coming with their own backplate. And with AM5, you have the backplate and the SAM, the socket actuator mechanism, and they are screwed together, so you cannot remove the backplate stock. That's not possible, which means that if you have a cooler that requires to use its own backplate, and we can do some research quickly just to get an overview if there are a lot or maybe just one, then if you have a cooler that comes with the backplate, it's not compatible out of the box and you will need to use some kind of adapters. I didn't do a lot of research, I just checked some quite popular coolers, for example the EKW Quantum Velocity cooler that is coming with an EK backplate. That is not going to be compatible with AM5. Same goes for the EK Magnitude, which is also a quite expensive block from EK. But also EK stated online that they will be working on an adapter kit, so for the future it should at a certain point be compatible to AM5, at least once you get the adapter kit. Same thing I found for EKL with, for example, the Brocken 3. That is also coming with its own backplate, but I could not find any kind of information about an upcoming adapter kit or not. Cooler Master is also listing several coolers online that out of the box will not be compatible with AM5, and you will need an adapter kit. But just looking at today, which is not even 1 week away from launch, I could not find any adapter kit for AM5 online for purchase. This means that if you want to get AM5 right at launch and you have one of the affected coolers, you might have to wait for getting an adapter kit, or you might have to switch to a different cooler. And that's one thing you can debate if that was necessary or not, but generally speaking, AMD had to use a much thicker IHS to maintain compatibility. And that is something I'm not quite sure if that was a correct or like an intelligent move. Simply because it's now so thick that your thermals will suffer from this. If we just measure the edge of the IHS to the edge of the SAM, you will see it's about 1.5 millimeter difference. So we could easily take off like 1.2 millimeters of the IHS And this way get better temperatures, because if your heat has to travel through more material before it's getting dissipated by the cooler, the temperatures of your cores will suffer. And I'm not sure if it was the correct move from AMD to like maintain cooler compatibility in theory, because we know it's not like full compatible depending on your mounting, and thus then have maybe worse thermals on this platform and also like upcoming AM5 CPUs, because dimension wise they will be obviously the same. Not quite sure, but I think maybe let's just check some random coolers if they're compatible or not. Now we are going to apply some liquid metal both on the I/O die and also on the other chiplets that are containing the cores. And on the CPU block we also pre-applied liquid metal. Now moment of truth, let's see if it powers up. Looks good, I think. Getting in the right direction. And also the idle temperatures so far look promising, even though it's 35 degrees Celsius, but you also have to consider that I'm running a rather high voltage. Moment of truth now, because that's the first time running load with DirectDi for me. I have no idea what kind of temperatures we will see, if the contact is good or not. Bear with me. Okay, right now I'm not sure what to say. Like, the temperatures improved by more than 20 degrees Celsius. Like, is this real? It's like 70 load. I'm just rerunning the third time now. But you can see those temps are real. They're increasing now slightly because definitely we're putting more heat inside the radiator, but it's in line. And also package power is a bit lower. It's like 15 watt lower than previously, but that is due to the lower temperatures. That's in line. We are running the same BIOS profile, same voltages, same everything. What we also want to know is if this helps gaining more frequency previously, even without raising the voltage. 5450 MHz would instantly crash. And it's running. So 50 MHz gain is already there. Now that we're not thermally limited anymore, we can apply more voltage. I increased by only 30 millivolts. And now we can run 5.5 GHz across all of the cores under load. That is just an insane frequency for 12 cores. After seeing those results initially, I thought that's kind of unreal. And I double checked and like triple checked literally everything. Like the mounting, I checked all the settings, I checked if the performance is there, but you could even see this yourself. If you're just going back and watch it really in detail, you will see that the performance in R20 is identical. So it's not like some cores are maybe clocked to a different level, and also the voltages are identical. I'm running the same BIOS. I didn't even use the platform for anything than just this testing. So it's the same profile, same voltages, same everything. But still, if we look into the chart, depending on the exact point for comparison in this R20 run is between 18 to 21 degrees Celsius temperature difference. And I already normalized to the same room level because today it's a little bit colder. The initial testing we did was more in summer. And that's why I had to normalize the testing from today, increase the temperature slightly by a bit over 2 degrees Celsius to just have the same kind of level. But still, we still have between 80 and 21 degrees Celsius lower temperatures. That is completely insane. I did not expect this. I expected maybe like 10, 12 degrees Celsius. Those are the results we typically had before. But I also want to point out that this is pretty much the first time doing DirectDi on AMD, because previously we only had DirectDi on Intel, never on this platform, so it's also something completely new. I also want to highlight for transparency that I was using Conductor Node Extreme liquid metal, which is not available on the public market yet. It is a bit better than the conventional liquid metal, than all conventional liquid metals you can find right now. It's an in-house development from our side. It will hit the market soon. This will not give you like 10 degrees Celsius lower temperatures though. This is maybe like 1 to 2, maybe at best 3 degrees Celsius better than the previous liquid metal. So that's not responsible for the huge temperature gain, but just for like full transparency, so you know what I was using. It's still a surprise to me to see like 20 degrees Celsius lower temperatures, and then getting 100 megahertz more out of the CPU, and I guess there is still headroom for more. But even at 5.5 gigahertz, the CPU peaked out at 73 degrees Celsius, which means there is still thermal headroom to increase the voltage further, and this way maybe even get a higher performance than what we already saw. But generally speaking, AM5 to me is a lot of fun, very high performance, very high clocks. A lot of things we can modify, that's why I personally really like the platform, a lot of things we can try. There are more things we will show, but first of all we wanted to focus on delidding and doing direct die. Right now the state of both products is that they're in the final state, both are going to be in production in the next days. There's also something I don't want to hide from you, because during those development phases, especially for delidding for example, not everything always goes according to plan. We try different things, different mechanisms, different dimensions, and for example with the 7700X it didn't work out, and that's something you can now watch at the end of the video. And I just want to point out that there will be a second video coming from us in about 5 hours, and that will be with the 7950X, some overclocking also with dry ice, so that should also be quite exciting. Thanks for tuning in, see you next time, enjoy the additional footage, bye bye. So first step again, placing the CPU inside the delider. And second step, slider goes on top. And in this version we also have our bearings placed inside here. I hope this will be a little easier. Nice, 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 nice. The first one was very, very smooth compared to the 7950X. For whatever reason, the slider just moved very quickly. I'm not quite sure if it's already delidded, but it felt a bit weird. Now I can see what the problem is. Yep, RIP 7700X.